Hi students, welcome to Max Point of View. Today we are going to understand the concept of magnetic effect of electric current. This is part A of electromagnetism. Here in this video, we are going to understand each and every concept of magnetic effect of electric current. Then we are going to solve each and every theory questions. So first understand the concept, then directly go to the theory solution, because here you will get the concept knowledge, but there you will understand what kind of questions they will ask, how to answer it precisely. All those things are taught properly. Like this you have to do for all the remaining parts, then you will get the complete knowledge without touching the textbook. All these videos are available in the description box. So without wasting any time, we'll start with our concept. There was a scientist called Hans Ørsted. In 1820, he was conducting an electrical experiment. During the experiment, he observed that a current carrying conductor, any conductor which is carrying a current, has magnetic field around it. So based on this one, he conducted many experiments, and at present situation we are taking so much of advantage of these kind of experiments. So before directly going to the topic, so we got to know that when a conductor carrying current, it has magnetic field around it, correct? So now before jumping into the topic, we are going to understand how to find the direction of that magnetic field because of electric current. So once we learn that, then we can aramse go to the topic so that we can find the direction of magnetic field. See, whenever there are two possible ways. Okay, first, okay, vertical and horizontal conductor. So assume a conductor carrying current like this. Okay, in this direction, a current is going from down to up, here from left to right. Here what is the main difference? The way you hold the hand, that is important here. And keep this in mind whenever we talk about direction of magnetic field because of current. There is one law we are going to use. Which law is that? Right hand thumb rule. Right hand thumb rule, nothing other than that. Okay, we have many other rules, but in our textbook that is only mentioned right hand thumb rule. Why I have to stress it like this? Because many students, instead of writing right hand thumb rule, they'll write right hand rule, thumb rule. No, right hand rule we can use any fingers, correct? Thumb rule we don't know which hand, right hand or left hand. That's why you have to clearly specify right hand thumb rule to find the direction of magnetic field because of the current. Due to current, it is only right hand thumb rule. Many students will write Fleming's left hand rule, Fleming's right hand rule. No, those are for different application. Just to find the direction of magnetic field, okay, due to the current, it is always right hand thumb rule, nothing other than that. Now, okay, now listen. So here whenever we have two types of conductor, straight conductor, one vertical, another one is horizontal. How to hold it, that is very much important. Listen, see, now whenever a current is flowing through a conductor, okay, magnetic field will be around it in both the ways. Magnetic field will be around it. Okay, now in which direction? So when it comes to vertical, okay, vertical conductor, we talk about whether it is clockwise or anti-clockwise. See, remember these points. Whenever we talk about vertical, okay, vertical conductor, we talk about whether the direction of magnetic field is clockwise or anti-clockwise. Whenever we talk about the conductor which is horizontal, we talk about north, east, south, west, all the four directions. We talk about all the four directions. Here the only possible ways current can flow in upward direction or downward direction, correct? And here the direction of magnetic field will be anti-clockwise or clockwise. But when it comes to a rod which is horizontal, okay, current can flow. So here we are going to use north, east, south, west, all those things, all the directions. Okay, so here how to hold it for vertical. First we'll learn for vertical, then we'll go for horizontal. See, which law we are going to use? Right hand thumb rule, correct? Whenever we use, okay, the vertical rod, vertical conductor, you have to hold it like this. You have to hold it like this. Okay, this thumb represents the direction of current. You have to hold it like where the current is going. If the current is going downward direction, see, if the current is going like this, you should not hold it like this. This thumb represents the direction of current, right? So you should hold it like this. You should hold it like this. So because the current is going downward direction, this thumb has to go down. So yeah, first you have to hold it like this or like this based on the direction of current. First we'll learn it for upward direction. For downward direction, exactly opposite. That's it. So you hold it like this. This thumb represents the direction of current. See, it should be like this. Then these fingers will tell us in which way it is going to rotate. See, it is going towards right, correct? It is going towards right. So the direction of magnetic field will be like this. If this is like this, okay, this will be clockwise direction. How can we say it is clockwise? Okay, listen, whenever you have a coil, okay, whenever something is rotating like this, if you see from the top, see, you try it. Whenever you try it, then only you will understand all these things. So whenever something is rotating like this, see, towards right side, correct? This is going towards right side, okay. So when you see from this angle, top view, okay, it is not clockwise. I told you, whenever the current is going upward direction, okay, upward direction, if you hold it like this, okay, if you hold it like this, it is clockwise, okay, the direction of magnetic field will be clockwise. But if you, whenever, see, the direction of magnetic field is towards right side, it is going towards right side. If you see from top view, it is anti-clockwise. It is not clockwise, but I told you it is clockwise. So how to conclude it? Very simple. You have to see from the angle where the current is coming from. Current is not coming from upward to downward. It is coming from down to up, correct? So you have to see from bottom view, okay, bottom view. So when, see, hold it like this, it is moving towards right, towards right. Now see, towards right, exactly like this. So whenever it is moving, you have to see from the bottom, then it will be clockwise. So always whenever we want to find the direction of magnetic field, we have to see from where the current is flowing, okay. So now the current is flowing from down to up, so we have to see from the bottom point, bottom view, then only you will get the proper. If you see from the top view, clockwise will be anti-clockwise. That's why you have to be very careful. So you have to see from the bottom view if the current is coming from bottom to top. Now the same thing, if the current, okay, if the current is coming like this from top to bottom, the same right hand thumb rule, you should not hold it like this, you should hold it like this, you should hold it like this. This represents the direction of current. It is going down, correct? It is going down. Once you hold it like this, this fingers represents the direction of magnetic field. So it is coming towards me, that is towards left. So the direction of magnetic field will be like this. This is anti-clockwise direction. And now you should not see from the bottom, you should see from the top, because current is coming from the top direction. So these are the simple procedures how to identify. So instead of all these things, very simple, remember only one thing. If the current is coming from bottom to top, it is clockwise, that's it, okay. And one more thing, if it is clockwise, it is south direction, keep this in mind. If it is clockwise, it is south. If it is anti-clockwise, it is north direction, north polarity. So all these things you should know. Don't learn both the ways. See, if one way is opposite to the other way, you don't have to learn both the ways, correct? So you learn only one, okay, the remaining will be exactly opposite. Now we'll go to this one. Okay, here we are not going to talk about whether it is clockwise or anti-clockwise. When the conductor is horizontal like this, we don't talk about whether it is clockwise or anti-clockwise. We talk about south, east, west, north, south. Okay, now listen, whenever, most of the time, 99% of the time, so they will tell whether this is south and this is north, south and north. So then you will get confused. If it is horizontal like this, see, like this, it has to be west and east, correct? But they will turn it like that. See, when you this is the original directions, correct? So we want south on the left hand side and north on the right hand side. So what I'm going to do, I'm going to rotate it like this. I'm going to rotate it like this. Okay, you can rotate like this also. If you follow the method which we have learnt, right hand thumb rule, if you rotate it like this or like this, you will get the same answer. I am going to show you both the ways. Now listen, so south is on the left hand side, north is on the right hand side. So when you rotate it like this, this west will go to the top point. This west will go to the, see, if you rotate it like this, west will go to the top and east will come to the bottom. Remember this point. Okay, now according to this diagram, south, north, west, east. Okay, because in the exam they are going to give you the questions like this. If you understand like this, then you will find it difficult. That's why you have to be learn everything. Then whatever the question they ask, if you have the knowledge, you can answer any question. Now listen, now once the current is flowing, okay, now we have going to use the right hand thumb rule only, but here we are not going to use, see, here we are not going to use it like this. We are going to open like this. Okay, only for the conductors which is horizontal, if it is horizontal, we are not holding like this, we are opening the fingers. We have to hold it like this only for both the cases, but here you are going to get confusion. That's why I am showing like this. So this will work for all the cases. So in this video we are going to learn many tricks, and those are not the actual method to find the direction of magnetic field, but as it is a 2D diagram, 2D, see, this is a 3D picture, correct? In all the angles you can see, but when it comes to the diagrams we cannot see. If you go back and see, you cannot see the picture only, correct? That's a 2D diagram. That's why these kind of tricks are very much important. So now, so when the current is flowing in a horizontal conductor, instead of holding like this, you have to hold it like this. So again, this thumb represents direction of current, and keep one thing in mind, this palm, okay, your palm has to be in front of you all the time. You should not hold it like this. Okay, this back side should not face you. Okay, all the time, whenever you're finding the direction of current, this palm, okay, has to be in front of you. Okay, this is the proper way. Okay, now so you have to hold it like this. Why? Because, see, why I'm holding like this, because this thumb represents the direction of current. It is going towards right, the current is also going towards right. That's why I'm holding like this. Okay, if the current is coming from this direction, see, I'll teach you all the method. Okay, so you have to hold it like this. Why? Because the direction of current here, it is towards right. This is the thumb also should be towards right. So once it is like this, the direction of magnetic field will be upside. Which is upside now? West. So here the answer is west. The answer is west. That's it. Now what I told you earlier only, some students, instead of twisting like this, they'll twist like this, correct? In that way also you are going to get the same answer. Now listen, if you twist it like this, so this side will be north and this side will be south, and we know in the first case we learned the current was flowing from south to north, correct? In the same way only we are going to learn we can apply in any direction. Okay, I'm just wanted to show we are going to get the answer west only. Okay, once you turn it like this, okay, the west will go downwards, correct? See, this is south, north, east, west. When you turn the original direction like this, the west goes down. So this is the same method. Okay, the current is again flowing from south to north only. This time the current is flowing towards left. So see, I have to hold it like this, right? No, it is completely wrong. Why? Because I told you, whenever you are holding, this back side should not face you. Okay, always whenever you are finding the direction of current, this palm, okay, this palm has to be in front of you. Now instead of holding like this, we have to hold it like this. So now this palm is facing us, and this thumb represents the direction of current. So where is the fingers showing? Towards downward. What is downward? That is west direction. So again our answer is, that's it. See, the important thing is how to hold your hand whenever it is vertical and horizontal. It is very much important. And one thing, in vertical we're not going to find north, east, south, west. We are going to find whether it is clockwise or anti-clockwise. Hans Ørsted was conducting this experiment only to find whether the current carrying conductor has a magnetic field around it. So for that we require only few things: battery, rheostat. See, rheostat we use. What is rheostat? First you should know. Okay, the symbol is RH. Rheostat is nothing but a variable resistor. So you can vary the resistance. So we know resistance and current are inversely proportional. If I increase the resistance value, current value decreases in the circuit. If I decrease the resistance value, current value increases. Just for that purpose, we have rheostat in the circuit. And we know the function of switch. Just to turn on or turn off the circuit so that current flows. When you open it, this is the open circuit. Okay, when you close it, when you tap on it, this will close. Okay, current starts flowing. This is the only purpose, is to turn close or open the circuit. That's it. Then we have a compass needle. See, this compass needle, you need to understand, whenever it is in the space, not on earth, it is in the space, it can, okay, it can show any direction, it can lie in any direction. But when it comes to earth, when the same compass is brought to earth, it rests in north-south direction because of the earth's magnetic field. Now anyhow this is on earth. Now at present it is showing north-south direction. This, see, this head will show the north. This is the north side. This tail will show this is the south side, like this. Okay, now so it is again connected to the negative terminal. Don't worry about this arrow mark. This is how we show the rheostat. If I connect this wire like this, okay, normally just to complete it like this will become a resistor. So that's why, just to show the difference between resistor and a rheostat, it is connected like this. So in all the 4 diagrams, this is what we are going to do. See, first we are going to learn only these two. These two will be exactly opposite. My suggestion is always don't learn everything. Don't learn everything. Just remember to the remaining whatever they talk. Okay, you need to understand the position of compass and the direction of current. These two are very much important. From where to where current is flowing. Okay, see, now this, for this diagram, plus is here, so current starts flowing. We don't care about all these directions. We don't care about all these directions. Where is the compass? Compass is here. Where is the wire? Wire is above it. So in this direction, this, see, only this part is enough. In this part, where is the current? It is towards right. Okay, next here current is coming from this direction, right? So the current is flowing in this direction. We care only about two things: from which direction is current coming from, where is the compass, whether it is below or, like in this case, above. Okay, those two are important. First we'll learn for below. Above will be exactly opposite. So in exam you have to be very clear. Okay, you have to observe all the words properly, whether the compass is below or above. First we'll learn for below. Above will be exactly opposite. Now listen, whenever the current is flowing, okay, in this direction, okay, we have learned the method to find the direction of magnetic field, correct? So when it is a horizontal, see, very important, horizontal conductor. So whether we have to hold it like this or like this, we have to open it. Okay, because it is horizontal, it is, this method is easy to understand. Now listen, current is flowing in this direction towards right, so you have to hold it like this. I cannot hold it like this because current is not flowing towards me, it is going towards right, that side. So I have to hold it like this, and always this palm has to face you. You should not, see, this is also correct according to you, correct, because this represents the direction of current. But what about this back side? This you should not face it like this all the time. This palm has to be in front of you. See, current is flowing towards right, you have to hold it like this. Towards up, you have to hold it like this. Towards left, you have to hold it like this. Towards bottom, you have to hold it like this. You should never hold it like this. Okay, this back side should not face you. Okay, this is one condition we have learned. Now listen, current is flowing towards right, so you have to hold it according to this. See, once you learn the concept, within 10 seconds you will get the answer. Now listen, current is going towards right, so this represents, okay, upward direction. See, in every question they will give you, okay, one particular direction. If this is not given, we can go for north, south, east, west direction. If that is not mentioned, okay, somewhere in the diagram or in this kind of things will be given in the question. Okay, if that is nothing is mentioned, then we can normally go for north, south, east, west directions only. Now in this question, current is flowing from south to north or north to south, that's it. Okay, horizontal conductors. Okay, now in this case, see, current is flowing from south to north. So from this angle to left to right, left side is south, north side is right. So current is flowing from south to north. You have to hold it like this. These fingers are showing upward direction. So what is upward? West. So in this diagram, the deflection of compass needle, is towards west, not upward. It is towards west. Okay, so few things we need to know. When the circuit is open, no current will be flowing. If the no current is flowing, this compass needle will rest in north-south direction due to Earth's magnetic field. That you should know. And you need to understand one thing, that this compass needle will deflect according to the magnetic field. If the magnetic field is showing west, it will deflect towards west only. If the magnetic field is towards north, it will deflect towards north only. Okay, so all these things. And one important thing, we are using rheostat. What is the purpose of rheostat? To increase or decrease the resistance so that current can be varied. Now if you want to deflect this compass needle more towards west, we have to increase the current. If you increase the current, more magnetic field will be produced. Keep this in mind, current and magnetic fields are directly proportional. If you pass more current, more magnetic field will be there. If more magnetic field is there, more deflection will be produced. So how to achieve that? We know resistance and current are inversely proportional. If you want more current, we have to reduce the value of resistance, okay, in the rheostat. So more current will flow, more deflection will be there. If you want to reduce the deflection, we have to increase the resistance so that current will be reduced. If current reduces, we know current and magnetic field are directly proportional. If current reduces, magnetic field also reduces. If the magnetic field means magnetic strength, okay, magnetic strength will reduce. If the magnetic strength is reduced, the deflection will also reduce. It will be moving towards left slowly, okay, only this much. If you pass more current, it will show deflection like this. Okay, all these things you should know. Okay, next, now we'll go to the second diagram. Here also the compass is below the wire only, below the wire. Now listen, here the plus is towards right, here the plus is towards left. So the current will pass from this direction, and we never care about these parts. We care only about this horizontal part. Here, where is the current? That is important for us. Now the current is flowing from north to south. So the direction of current is towards left. So initially here it was towards right. That's why we held it like this. Now the direction of current is towards left. So you have to hold it like this. So this thumb represents north. See, always this palm has to face your side. So that's why I'm holding like this. Okay, this thumb represents the direction of current. These fingers represents the direction of magnetic field. So downward it is east. So in this case, it is the deflection of magnetic needle is towards east. That's it. So you know how to increase the deflection, how to reduce the deflection, all those things we learnt in first diagram, correct? Now here in this case, so both the diagrams are same. Here what is the only change? The compass needle is below the wire. Here it is above the wire. That is the only change. See, assume this is the compass needle. Okay, this is the wire. Okay, the first case we are learning, assume my hand is the wire and this is the compass needle. Okay, now because of the current is flowing in this direction, it is showing the deflection in the compass needle showing west. Now if I place it above the wire, okay, I'm not going to do it like this, I'm going to do it like this. Okay, I'm going to place it like this, so upside down. That's why the direction changes. We are not going to hold it like this. So in this case we got west, right? Here we are going to get east. In this case we got east, right? So we are going to get west. That's it. So always in the here also don't learn both these above cases. Okay, learn the below case only. Okay, when the compass needle is below the wire, everything this will be exactly opposite to this one. These kind of things you have to be very careful. You should not learn all these things. See, if you have that very good memory power, you can always go for all the 4 diagrams, or else you learn only one method, these 2 diagrams. Okay, current flowing from left to right and right to left, then these two will be exactly opposite. But in the exam you have to be very careful where is the needle is placed, whether it is below or above. Few concluding points we need to learn based on Oersted experiment. See, very simple. These kind of questions will be asked in the exam. Why there is a deflection in a compass needle when the compass needle is brought near to a current carrying conductor? Very simple answer. Because of the current in the circuit, magnetic field will be created. That magnetic field influence the deflection in the magnetic needle. That's it. Next expected question. Whenever the compass needle is brought near to a current carrying conductor, in which way it will deflect? It will always deflect in the direction of magnetic field in the circuit. If in the magnetic field, okay, in the circuit, what is the direction of magnetic field? The same direction will be shown in the compass needle. What happens if you reverse the direction of current in the circuit? If you reverse the direction of current in the circuit, magnetic field will also be reversed. Magnetic field will also be reversed because those two are directly proportional. And one more question. If you increase the current in the circuit, what happens to the deflection in the compass needle? See, how to increase the current, that you should know. By reducing the resistance in the rheostat. If you reduce the resistance in the rheostat, current will be increased. If the current is increased, magnetic field, okay, in the circuit will also be increased. So the deflection will also increases because current and magnetic field are directly proportional. Now we learn about magnetic field in a straight current carrying conductor. See, now see, whenever they talk about circuits, whatever the circuits they give in the exam, the diagram, don't worry about it, because you need to know the functions of the devices which we are using here. See, here initially in previous experiment I used only one positive, one negative. Here one positive, one negative, one positive. So two positive, two negatives. So there we used it as cell. This is one cell. When you combine two or more cell, it becomes a battery. That's it. This is a cell. This is a battery. That's it. And we know the function of rheostat, correct? RH. And initially we used a symbol like this. That is a switch, correct? This is also a switch. The function is same. Okay, if you see a dot here, that is a closed circuit. So that means if you see a dot here, that means there is a connection here, from here to here. There is a proper connection. If you don't see a dot here, that means it's an open circuit. There is no connection between these two lines. That's it. Okay, if you analyze the diagram like this, you will not feel that burden. So first understand the diagram. That's it. So once you understand all these things, the important thing is we are going to learn where will be the direction of magnetic field in a straight wire. Okay, now listen. Whenever you close the switch, current starts flowing, correct? But we don't care about all these directions. We care about, this is a straight wire, right? So we care about the direction of current only in this path. So in all these paths we don't have to worry about it. So only this direction is enough for us. Okay, now the current is flowing in downward direction. Whenever the current is flowing in downward direction, see, in horizontal conductors, so this is not horizontal, this is vertical, right? So in vertical we have to hold it like this, correct? In horizontal you have to open it like this. Now anyhow it is vertical, we have to hold it like this. And you, do you think this is correct? No, this is wrong. Why? Because this thumb represents the direction of current. See, the current is flowing downward direction, so you have to hold it like this. You have to hold it like this. So if the current is going downward direction, these fingers will tell us the direction of magnetic field. So it is towards me, towards left, correct? So now listen, so we got to know it is towards left. Now what we are doing actually here, so before passing the current, this is the cardboard sheet, this is the cardboard sheet. Now on the cardboard sheet we'll sprinkle some iron fillings, small iron pieces, okay, small iron pieces, those are called iron fillings, okay. When sprinkle it, now once you turn on the current, there will be no change in the arrangement of sprinkles. There will be random direction in as in the earlier stage when you sprinkle it. Now just tap on the cardboard sheet, these iron fillings will start arranging themselves in a circular path, not only one circle, many circles. So these kind of many circles we call it as concentric circles. So whenever a straight wire carrying a current, iron fillings arrange themselves in a concentric circles, keep this in mind. So anyhow we got to know current, you have to hold it like this because the direction of current is towards downward. So these represents the direction of magnetic field, it is towards left side, So what are the things we need to understand here? Okay, well, first thing, if you increase the current, what happens? We know if you increase the current using the rheostat, okay, by reducing the resistance, the current will be increased. If the current is increased, magnetic field increases. But how we can see the increased magnetic field in a concentric circles? The diameter of the concentric circles will increase. That means that it becomes denser. These magnetic field, okay, these iron fillings will arrange themselves, okay, will grow in size. That means you can write it as it becomes denser, or you can write it as the diameter of the concentric circles increases. That will show us the magnetic field also increases. So this is a very simple experiment, as this is there in a textbook, we are learning it, okay. Anyhow we have learned right hand thumb rule, how to use it also. Now we learn about magnetic field due to a current in a loop. So if you take a loop, a circular loop wire, okay, and if you take a cardboard and make two holes according to the sizes of this loop, okay, now this loop is inside this cardboard. So now we are going to sprinkle some iron fillings, just sprinkling them, and the circuit is open, okay. No current is flowing, so no change in the direction of, no change in the arrangement of this iron fillings. Once you close it, okay, once you close the circuit, the current starts flowing, okay, now what happens to the arrangement of these iron fillings? Nothing will happen until you tap on it. So once you tap on it, these iron fillings which is there on the cardboard will start arranging themselves in a circular path, okay, in both the holes, okay, here also, okay. Now assume this is a point P, and this center is point P, and this center is point Q. The vicinity at P, what do you mean by that vicinity? Vicinity is nothing but nearby. What do you mean by that? Vicinity is nothing but nearby. Vicinity at P means nearby P, the point P, nearby the point P. So the circulars, okay, the circle which is very close to point P and point Q, okay, vicinity at P and Q means the near points of P and Q. So P and Q, nearby P and nearby Q, the iron fillings are almost circular in shape, exactly near to P and cube. Okay, that is nothing but nearby. Instead of using nearby, they are using vicinity. That's it. Okay, now listen. Now the current is going here in this direction, upward direction. If the current is flowing upward direction, we have to hold it like this. See, it's a vertical. Okay, whenever it is a vertical, see, it's vertical, right? Okay, whenever it is vertical, we have to hold it like this. If it is horizontal, we should hold it like this. Okay, we should open it. Anyhow, it is vertical, we have to hold it like this. This is the direction of current, and these fingers will represent the direction of magnetic field. So this side, okay, this side, it is towards right side, towards right side. Okay, and we learned whenever it is going up, when the current is upward direction, that is clockwise. What is the direction of this one? Clockwise. If it is clockwise direction, it represents south. Which polarity is that? South. And this side, current is coming in downward direction, correct? See, current is coming from this direction and going down. So at this point, it is coming, like it is going like this. Current is going like this. So these fingers will represent the magnetic field lines, that is towards left. Okay, and if it is downward direction, what is the deflection in the this one, iron fillings? That is anti-clockwise. Anti-clockwise. See, in some textbooks they use counterclockwise. Counterclockwise is nothing but anti-clockwise. If it is anti-clockwise, what polarity is that? That is north. That is north. And exactly, see, there are exactly at the center, okay, the direction of magnetic field lines will be like this. So exactly at the center, the field lines will be parallel to each other, exactly at the center. Okay, if you keep on increasing, okay, exactly at the center also we have some magnetic field lines. Okay, and here the magnetic field lines are parallel to each other exactly at the center. See, here also it is going upward direction, here also it is going upward direction. That's why these field lines are also going in upward direction. And so a few things we already know. How to increase the magnetic field lines here? Increase the current in the circuit. See, here we are using rheostat. That's why we can aramse increase the value of current. Next, what happens if you change the direction of current? If you change the direction of current, okay, if the current is flowing, okay, if you make this one right side one plus and this one minus, current starts flowing in this way. See, in this way, correct? If the current direction is reversed, every value will get reversed. This will become clockwise and that becomes south, and this becomes anti-clockwise and that becomes north if you change the direction of current. Now we learn about magnetic field due to current carrying conductor in a circular coil or solenoid. Circular coil is also considered this solenoid only. So any one word we should assume it as solenoid. When it comes to solenoid, many students will get confused. What do you mean by solenoid? Nothing else. This circular coil, this shape is nothing but solenoid. That's it. Okay, circular coil or solenoid. The same method we are going to apply here, so to get the direction of magnetic field. See, here we know all the functions of these devices. Correct. Now the current starts flowing like this. So once the current starts flowing, okay, it produces magnetic field. Now here, this solenoid, you need to understand one thing. Solenoid, whenever a current is given to a solenoid, it behaves like a bar magnet. Keep this in mind. Whenever the current is passed to a solenoid, this is a solenoid, right? It behaves like a bar magnet. We know in bar magnet, see, in bar magnet, if this is north and this is south, okay, the direction of magnetic field lines is from north to south. Outside it is north to south, inside it is from south to north, correct? And exactly at the center it becomes parallel. It goes like this. This is what we have done in our labs, correct? Okay, so this solenoid, current carrying solenoid, behaves like a bar magnet. Keep this in mind. If you know this one, aram se you can write this one. See, when the current flows in this direction, Okay, one of them will become north and south. How to identify whether this which is north and which is south, that we are going to learn in the next slide. For now you need to understand the direction of magnetic field, that's it. So next slide, immediately after this one, I am going to show you all the possible ways, all the possible diagrams, how to identify in a very easier way. Now listen, assume this is north and this is south. For now just assume, don't worry how it became north and south. Next slide I'm definitely going to teach you with all the possible diagrams. Assume this is north and that is south. Now we know this solenoid behaves like a bar magnet, correct? So all the lines in the bar magnet outside the bar magnet, it moves from north to south. So here the direction of magnetic field lines will move like this. See, it's going from north, okay, when it comes to south, from north to south. And okay, inside this solenoid, inside we have a gaps here, right? The field lines are almost straight, which are parallel to each other. So one thing, outside it is not parallel. Inside the solenoid, the field lines are parallel to each other. Keep this in mind. And whenever so I am going to teach you how to select north and south in the next slide. If it is north, wherever the north it is, okay, from the north it has to go outside. If this is north, okay, this side the arrow marks will be like this. North, it is going, okay, from the north. If this was north, these things you should know. And one more possible question, name a shape where its diameter is less than its length. When the length is more compared to the diameter, diameter is nothing but the thickness of the wire. If the thickness of the wire, nothing but diameter, is less than the its length, what is the name for those kind of shapes? That is nothing but solenoid only. If the diameter length, see, diameter is nothing but the thickness of the wire. This is smaller than the length, correct? The length is very huge, okay, compared to its thickness. Thickness is nothing but the diameter. If the diameter is less than its length, then it is a solenoid. And few students will get doubts, what if the diameter, okay, is greater than length? What do you name that shape as? Those kind of shapes are called pancake shapes. Pancake shapes are flat spiral coil. So those are the other names for if the diameter is greater than its length, but that is not there in the syllabus, so you don't have to worry about it. Now we'll learn how to increase the magnetic field in a solenoid. See, first thing is by increasing the number of turns. If the number of turns, see, this is called as one turn. These are number of turns. Few students will make mistake while writing the exam. Okay, what are the two ways to increase the magnetic field in a solenoid? They'll write by increasing the number of coils. Number of coils is completely wrong. See, this complete wire is one coil. Okay, so it is not by increasing the number of coils, it is increasing the number of turns of the coil, or you can write it as by increasing the windings of a coil. Windings are nothing but number of turns only. Then what is the other way? By increasing the current in the circuit. If you increase the current, we know that, right? So by increasing the current in the circuit, magnetic field will also be increased. And how to achieve that? By increasing the current, by reducing the value. Keep this in mind, very important question. See, assume the diagram is given. Okay, the diagram is given and you have to find north, south, all those things. I told you I'm going to teach you north, south, how to find the north and south of any diagram, okay, after we finish this solenoid topic. Okay, next we have the similarities between bar magnet and solenoid, advantages, all those things. After that, immediately we are going to learn how to identify north and pole. That is very, very important, and if you know the logic, it is very easy. Within 10 seconds you can get the answer. Now for now, okay, so we were talking about if you decrease the value of resistance. So this is very much important. If rheostat is given, okay, by decreasing the value of resistance, current can be increased. This is what you have to write. If the diagram is given, okay, and rheostat is there, so state one possible way to increase the magnetic field in the solenoid. But here if it is a diagram given, you cannot increase the number of turns, correct, because the diagram is already given, correct. So number of turns will not come into the picture. Then what is the only possible way? Increasing the current. How to achieve that? By decreasing the value of resistance in the rheostat. This is what you have to write. By decreasing the resistance in the rheostat, current can be increased, so that magnetic field also increases. This is what you have to write. If you don't mention anything about resistance whenever the diagram is given, you will not get marks. And one more possible question: how to increase the magnetic field in a solenoid without increasing the number of turns and without increasing the value of current? How to achieve that? So these kind of questions also possible. These kind of questions are called logical questions. So what is the only possible way? That means we know there is a gap between the turns, correct? Gap between the turns. So in the axis, so here a few students will get confused about the word axis. What do you mean by axis? The word axis. So you take any shape. Okay, any shape. Axis of the coil, axis of the rectangle, all those means an imaginary line passing through the center. That's it. This is the axis, meaning of axis. So when it comes to axis, what do you mean by axis? The imaginary line passing through the center of any shape. That's it. So don't worry. See, this is what happens when you don't learn the meaning of words in physics. So you know, many students I have seen, they use many physics related word and they don't know the meaning of it. Like they'll use magnitude, the word magnitude that easily, and they don't know the meaning of magnitude. So whenever you use some word, just to make sure you know the meaning. That's it. Okay, now what do you mean by axis? Axis is nothing but the imaginary line. So inserting a soft iron in the axis of solenoid. Assume we are inserting a soft iron inside this solenoid. Okay, by inserting a soft iron in a solenoid, inside a solenoid, in the axis of solenoid, magnetic field will be increased. How that is possible? So very simple. See, these are the basics. These are the basics of electromagnets. This is nothing but electromagnet. So listen, this soft iron is a magnetic material. What do you mean by magnetic material? The material which gets attracted to magnet. Assume a nail. Assume this is a magnet and a nail. See, this nail is a magnetic material. In the same way, this soft iron is also magnetic material. So what happens is, when you attract this nail to magnet, this nail will also act as a magnet. That is a temporary magnet, correct? So because of this magnet, we have some magnetic field. When this nail attracts to this magnet, again this becomes a temporary magnet. So magnet plus magnetic strength increases, correct? Now when you place a soft iron inside a solenoid and when you pass the current, this soft iron will get attracted to solenoid. Once it get attracted to solenoid, this soft iron becomes a temporary magnet. So initially we have magnet because of the electric field, and we have converted this soft iron into magnetic field. So magnet because of the electric field, and magnet because of the soft iron. Magnet plus magnetic field increases. So this is one more possible way. This is the one possible way they can answer any question like this. So what happens if you insert a soft iron inside a solenoid? What happens? The magnetic field increases. That's it. Now we learn similarities between bar magnet and a solenoid. So very simple. We know whenever the current is passed to a solenoid, it behaves like a bar magnet. This is what we have learned. This is one similarity between solenoid and bar magnet. Then what happens? We know whenever a bar magnet is suspended freely, okay, bar magnet is suspended freely, okay, it always rests in north-south direction, correct? In the same way, when the current carrying solenoid, not just a solenoid, if you suspend a solenoid, it is just a conductor, it can rest in any direction. But when you suspend current carrying solenoid, not just solenoid, current carrying solenoid, we know it behaves as a bar magnet. So if you suspend bar magnet, it always rests in north-south direction. In the same way, current carrying solenoid also rests in north-south direction whenever it is suspended freely. And like a bar magnet, it attracts iron fillings. Whenever a current carrying solenoid is there, if we bring iron fillings near to the current carrying solenoid, it attracts them. So these are the similarities between bar magnet and a solenoid. Now we learn dissimilarities between bar magnet and a solenoid. See, in solenoid it is nothing but an electromagnet, correct? Because of the electricity, the magnetic field is created. So we can increase the strength of a magnetic field in a solenoid, but in bar magnet it is fixed, correct? As it is an electromagnet, solenoid is an electromagnet. If we increase the current, magnetic field will be increased, but bar magnet it is fixed. Then the direction of magnetic field, the polarities of magnetic field, north south, cannot be changed in bar magnet, but by changing the direction of current, we know that polarities north and south pole of a this one solenoid can be changed by reversing the direction of current. Now we'll talk about electromagnets. What do you mean by electromagnets? The normal conductor which will be converted into magnet by passing the electricity to it. This is the general definition. So how to define electromagnets? Electromagnets are temporary strong magnets created by passing the current through the coil which is wound around a soft iron. So around a soft iron, say assume this is a soft iron. Okay, coil is wounded around it, okay, like this. So when electricity is passed, this soft iron behaves as a magnet. This is nothing but electromagnet, and we know electromagnets are called artificial magnets. And many students will get this doubt: why we have to use soft iron only, why not normal iron, why not other magnetic materials? Why? Because soft iron has low retentive property. When these kind of questions are asked, many students will write a lengthy answer. Instead of writing lengthy answer, these keywords are enough. Okay, soft iron has low retentive property. So before learning that low retentive property, first we learn what is retentive property. Retentive property is nothing but, so assume if you take a normal iron or any other magnetic material, if you pass the current, it will gain the magnetic field, correct? But if you take out the current, immediately magnetic field will not go off. It will hold the magnetic field for some time. That is retentive property. Okay, for an electromagnet, it should have low retentive property. That means once you take out the current, there should be no magnetic field. The magnetic field has to go off immediately. That is nothing but low retentive property. So soft iron doesn't have retentive property. That is nothing but it has low retentive property. So instead of writing the lengthy answer, you can use these keywords to get the full marks. So when it comes to constructions of I-shape and U-shape magnets, constructions are not there, but based on the diagram, okay, we need to identify north pole and south pole of a U-shape and I-shape magnets. That is very much important. Those are very easy to understand. There are some logics, there are some tricks. I'm going to teach it now. If you understand the trick, within 10 seconds you can get 3 to 4 marks. First we will learn how to find the north and south pole, that is nothing but the polarities of a magnet in an I-shaped electromagnet. Now we are going to learn how to find north pole and south pole of a magnet for a different diagram. These are the only 4 possible diagrams. So based on this, we are going to learn how to find the north or south pole of a magnet. Okay, here electromagnet. Okay, so this is very much important. This is what they can ask. They can give you the diagrams. Okay, any one of the diagrams. These are the only possible 4 diagrams. So they can give any one of 4. Then they can ask you questions. If you know the knowledge, if you know the technique, around say you can answer any kind of questions. Once you gain the knowledge here in the concept video, then you will understand how the questions will be asked in the theory solutions. That video will also be available in the description box. So first we'll go with this one. Go with this one. Now listen. So the bigger one is positive, the smaller one is negative. This is very much important. Plus, minus, minus, plus. Once you write the plus and minus terminal, draw the arrow marks. The arrow mark of current. This is enough. So here also it's going up and coming down, because the plus for our current always flows from plus to minus. So here minus, so the current goes up and comes down. So here current goes up and comes down. Okay, now this is done. Now it is time to find the polarities of magnetic field. Now listen, first thing is whether the first line, this is the first line, right? First line of this wire, this complete wire, this is the first line. Always you start from left side only, left side of this wire, this wire, this wire. That is what we are going to learn. This is the first wire, correct? So the first wire is above the rod. See, this is above, correct? This is above. See here, the first wire is below, okay, behind, sorry, behind. Okay, here the first wire is above, here the first wire is from behind. This is very much important. This is what we are going to identify. Once you identify that, see here this first line is above. Once you find this is above, you have to hold it like this. If the first line is above, you have to hold it like this. See, this represents this all fingers represents the first wire. This is going above the rod. If you see a diagram like this, the first wire is coming from the behind of the bar, so you have to hold it like this. The wires are going, okay, coming from the behind of the bar. You have to hold it like this. This is the first step. Okay, so in all the cases, see, first we learn both these diagrams, then I'll teach you how to do with these two diagrams also. These are the only possible four. Okay, now once you got to know where this is above, right, you have to hold it like this. Now this thumb represents north sometime, south sometime. So how to identify that completely depends upon plus. Where is plus? If the plus is towards left, okay, listen, this thumb, whether this, like you're holding like this or like this is very much important. Listen carefully. If you are holding like this or like this, okay, this thumb represents north sometime, south sometime. That completely depends upon the positive terminal of the battery. If the positive terminal of the battery is like towards left, this thumb represents whether you are holding like this or like this. Okay, if the positive is towards left, okay, I'll write it like here. Okay, if the positive, okay, of the battery terminal is on the left side, left, see, this positive terminal is on the left side, here the positive terminal on the right side. Okay, then thumb, okay, is north. Thumb is north. Okay, the thumb is north. If the positive terminal on right, the thumb represents south. This is very much important. Listen, see, actually this is not the way to learn it. Okay, it depends upon whether it is anti-clockwise or clockwise, whether these circles are providing anti-clockwise or clockwise based on the direction of current. As it is a 2D diagram, this is very much difficult to understand whether it is clockwise or anti-clockwise. That is why I found a method. Okay, this method works on all the diagrams. I have tried it. Okay, you can also try, and you will also understand while we are solving the theory solutions. Okay, theory questions. Now listen, first the thing is plus is on the left side, the thumb represents north. Okay, this thumb represents north. If the plus is on the right side, you see here the plus terminal is on the right side, so the thumb represents south. Now first thing is you have to hold it. You hold it like this because the wire is above the bar, above the coil, correct? The first wire is above, so we have to hold it like this, and we have to see plus is on the left side or right side. Plus is on the left side, correct? If plus is on the left side, thumb represents north, so this will be north and this will be south. That's it. See, once you understand this logic, to find north and south will take only 10 seconds. In the exam, once you find the answer for north and south, writing will take 10 seconds. So these kind of questions will be asked for 3 to 4 marks. Within 1 minute, you can score 3 marks if you have the knowledge. That is what we are going to learn here. Okay. Now we'll go for the this diagram B. Okay, for second diagram. Now listen. So this, okay, don't worry about this diagram. See the first line is coming behind, from the behind the bar, so you have to hold it like this. Now this thumb represents north, sometimes south, sometimes, depends upon where is the plus symbol is on the left hand side, so this thumb represents north, correct? If the plus symbol is on the left, this is on the left, right? So thumb represents north, so thumb is, see, this thumb represents north, that means this side is north and this side is south. That's it. The same method we are going to apply here. Now, see the first line. See the first line. This is above. First line is above the rod, above the bar, correct? So you have to hold it like this. Now, this thumb represents north sometime, south sometime, depends upon the where is the plus polarity. Plus polarity on the right side. Okay. You see? Plus is on the right side, minus is on the right side. You hold it like this. So now if plus is on the right side, thumb represents south. If plus is on the right side, thumb represents south. Where is the thumb? That is left side. So this is thumb represents south and this is north. That's it. The same thing here. See the first line is coming from the behind. Now the thumb represents north south, depends upon the polarity of plus. So plus is on the right side. Okay, plus is on the right side. If plus is on the right side, thumb represents south. Where is south? South is that side, correct? South is that side. So right, south and north. Okay, see, this concept might be a little confusing for you, so go back and rewatch it. You will definitely understand. This is what very much important, because based on this one, any kind of questions, once you find north and south, they are going to place compass here and one more magnet here, and based on that they are going to ask questions. If you know this much, you can answer any question. Now we learn how to find the north and south pole. That is nothing but polarities of a magnet in U-shaped electromagnets. So few students will think these both are same diagrams. No, here there is a small difference. First we'll learn with this one. Okay, next we'll go for that one. And like a I-shaped magnet, okay, the horizontal electromagnet, this has a different trick. Okay, this has a different trick and this is easy compared to that one. Okay, here the first thing, again, it is not about the first line. It is not about the first line. See, this is here, the first line is above the U-shaped electromagnet, correct? U-shaped electromagnet. So here we don't care about all those things. When it comes to horizontal, the previous one we care about the first line, right? Here the simple thing is the direction of the current. See, here the direction of current is towards right side, correct? The first one, you don't have to worry about these direction and all. We don't care about all these things. We care about the direction of current on the U-shaped magnet. See here, right side, right side, right side, and this side it is left side, left side, left side. So important thing is both the sides. Okay, on both the sides the direction of current is opposite. This is towards right, this is towards left. That means one will be south pole, one will be north pole. One will be south pole, one will be north pole. There is one case where in both the sides, okay, on both the sides the direction of current, okay, toward both the sides it will be towards right, or both the sides it will be towards left. So in both the in those kind of cases, on both the sides we have same polarity. I am going to teach you that also. Now listen. This one, towards right, towards right, towards right. See, first thing, these directions will not be given. Okay, will not be given. You have to write according to that. How to write? See, the current is going here. On the this wire is on it, right? So the current is going here, and this is going back side and comes here, correct? And again this wire goes back side and comes here. So now we got to know it is on the right hand side. So it is facing towards right. If it is towards right, keep this in mind. If it is towards right, it is south pole. If it is towards right, it is south pole. And this side, continue it. Okay, I will write it for you now. So now continue it. The current, this wire is coming from the back side. We cannot see the direction of current. So we now from the back side it is coming. So here on the rod, on this U shape only we have to write the direction. See, towards left, towards left. So you don't worry about all these things. Only one arrow mark is enough. On the U shape, so these wires we can see on the U shape. This wire, this wire, this wire we can see. But here this wire is coming behind the U shape, so you don't have to worry about it. One direction is enough. So this side it is towards left, that's why this is north. If the direction of current is towards left, okay, it will see, if it is towards left, what happens, it is going to form anti-clockwise direction. That is how I am writing north. See, towards right. Now this is, if it is towards right, it is going to form a clockwise direction. If it is clockwise, we know it is south, that's why I am writing south. Okay, now we'll go for this diagram. We'll see how this diagram is different from the first one. Now listen, again see, the polarities of current is very much important. So current is coming from here. In this case also the current is coming from the positive terminal only, but here the first line is behind, we cannot see the direction of current. Okay, it is behind and coming here, correct? So the direction of current is like this. See, it is from the behind, it is coming and going like this. So the direction of current is like towards left. If this one is enough to find the pole. So again it is going back and coming here, correct? So towards left. Here from the back side it is going down, and from here it is going like this, and from the behind it is coming. The current is towards right side. If this is right side, this will also be right side. And I told you, if it is towards left side, it is going to form towards left side, anti-clockwise direction. If it is anti-clockwise, this is north. See, towards right side, so it is going to form clockwise. So if it is clockwise, that will be south. That's it. So if you find north and south, there will be two more sub questions will be there, like how to increase the value of magnetic field, all those things. Those things I know you can aramse answer. The first important thing is finding the north pole and south pole. And I told you there are some diagrams where you can get both the side south and both the side north. That is what we are going to learn now. These are the two tricky diagrams where most of the students will go wrong. See here, now the important thing is, now the current is coming from this direction, right? No, completely wrong. Why? Because the plus side is on the right hand side. If this plus side is on the right hand side, the current will start flowing in this direction, correct? So this is the first step. You have to see the polarities of the battery or a cell also. So from the plus the current starts flowing. Don't worry about all these things. From here it's flowing. Now once it starts flowing, it goes in this direction, correct? See, we only care about the direction of current on the U shape. This line is on the U shape, right? So this is important. So see, this wire is going back side, and the current, see, the current is coming like this in this direction. Again it goes back, again it comes here, it goes like this, and see, from the behind it is coming. From the behind we don't care. The wire has to be on the this U shape rod. See, it is current is coming from here back side and in this direction. See, the current is coming in this direction, going back and like this direction. See, in both the cases the direction is towards left, and this side also it is towards left. This is very much important. Analyzing these things are very much important. In some of the diagrams arrow marks will be given. 90% of the time arrow marks will not be given. You have to draw it so that you will find the direction. Okay, now we know both the sides on the left, the current direction is towards left. If it is towards left, okay, it is going to form anti-clockwise. If it is anti-clockwise, it is north. This side also north. That's it. And few students will be wondering, how can a magnet has both the sides north pole? Very simple. Assume there is a block of magnet. Okay, south, north. What I'll do, I'll make this block of magnet in this U shape. So I'll remove the extra part. All these things I have removed. See, now both the sides are south, this side will be north. That's it. This is how they are getting both the sides north as well as sometimes both the sides north, sometimes both the sides south. Now listen, now here first thing we need to see the polarity of the current. See here the current is flowing from this direction, okay, but in this case the current was flowing from right to left, but here left to right. This is very much important. Once you get this one, see, the first wire is not on the on this U shape, correct? It is behind. So see the first wire, see this is the first wire, current is going from back side and towards left. So here also it is towards left, back side it is going towards right, and again left, left, correct? So both the in both the cases, here also it is towards turning towards left, that means it is both the sides north. Sometimes you may get both the sides will be south also. So these are, see in the same diagram the polarities are different. This is what I wanted to tell you. The polarity is also very much important. If you start from here, everything will go ulta. See, if you start from here, according to you, if you start from here, this is the first wire, right? So you will write like this. If it is towards right, you will write it as south, and this side also it becomes south. The complete answer will go wrong. That's why the polarity of a battery or a cell is also very much important. What are the two ways to increase the magnetic field of an electromagnet? There are only two possible points. One is by increasing the number of turns of the coil. You should not write by increasing the coils. Increasing the coils is wrong, because we have only one coil. Just by increasing the number of turns of the coil, or by increasing the windings of the coil, we can increase the magnetic field of an electromagnet. What is the other way? By increasing the current, by increasing the magnitude of current in the circuit, because we know current is directly proportional to magnetic field. If current is increased, magnetic field also gets increased, and if you change the direction of current, magnetic field direction also, north pole, if you assume north and south, because of the current is flowing from this direction. If you change the current direction, okay, in opposite way, north and south pole will also get reversed. So if you reverse the direction of current, polarities of a magnetic field also reversed. Now we'll know few things about permanent magnet. Most of the permanent magnets are naturally occurring. If you are making it, we are using steel. It is so permanent magnets are made up of steel. So why steel? Why not other materials? Why steel? Because it has more retentive property. More retentive property. So in the previous slide we have learned a few things about retentive property. Retentive property means once you give the electricity, okay, it will be converted into magnet, correct? But once you take out the electricity, it will hold the magnetic power for a longer period of time. That is nothing but retentive property. Okay, so steel has more retentive property, so it is used as permanent magnet. Okay, once you take out the electricity also, it has to hold the magnetic power. That means electricity is providing the magnetic field, correct? So whenever we provide a magnetic field to steel, it will hold, okay, not only through electricity, in other means also. If we provide if you convert a steel into magnet, it can hold the magnetic power for a longer period of time. That is nothing but retentive property. Retentive means holding it for a longer period of time. That is why we are using steel. Why not soft iron? Because soft iron, we know it has low retentive property. These kind of questions you can expect in the exam. Why not? So why we are not using soft iron for permanent magnets? Very simple. A soft iron has low retentive property. Why we are using steel? Because steel has more retentive property. Then what are the uses? So where these permanent magnets are used? These are, for example, these are used in galvanometer, ammeter and voltmeter, even the compass needle. In compass needle we don't use electromagnets, we used permanent magnets. Okay, compass. Okay, these are the uses. And why we have to use magnets in galvanometer, ammeter and voltmeter? See, very simple. Whenever you place a magnet, normal magnet and electricity, okay, whenever we combine both these things, a force will be generated. That is what we are going to learn in part B. Okay, just remember this. Whenever a magnet is the normal magnet and electricity, whenever these two are combined, a force will be generated. Based on the force only, okay, how much current is flowing through a circuit we can find, how much voltage is flowing through a circuit we can find. That is why we use, okay, permanent magnets in galvanometer, ammeter, voltmeter, and we know why we use magnets in compass. Now we'll learn the differences between electromagnets and permanent magnets. Very simple. First we'll go for made of. Okay, these electromagnets are made of electromagnets, soft iron. Permanent magnets, those are made up of steel. Okay, and these electromagnets are temporary. Okay, but when it comes to permanent magnets, these are permanent. Temporary magnetic field, you can write it as electromagnets can provide temporary magnetic field. These can provide permanent magnetic field. But in the exam, you should not use the short form MF, all those things. No short forms in the exam. And these generally electromagnets are stronger. Okay, in the exam you should not write like this. You have to write it in the form of sentence whenever you are differentiating between two physical quantities or any two objects. Okay, electromagnets are generally stronger, these are weaker. Okay, next, strength of a magnetic field, strength of an electromagnet, strength of an electromagnet can be changed by changing the current. Here it cannot be changed. Don't write X in the exam. It is just opposite to this one. Next, so here polarity can be changed. Polarity can be changed by reversing the direction of current. If you reverse the direction of current, polarity can be changed. Here it cannot be changed. And demagnetization is easy. Demagnetization is easy. Here it is not easy. That's it. Advantages of electromagnet over permanent magnet. It is very simple. Most of the advantages we have learnt in differences only. So first thing, these electromagnets are strong magnets. Generally they are strong. Strength of a magnetic field can be increased by increasing the current in the electromagnet. Then polarities of the electromagnet can be reversed by reversing the direction of current. These are the advantages. Electric bell. See, electric bell construction, working and all, nothing related to electric bell is there in the syllabus. But while solving the theory questions, we will learn few logical questions about electric bell, because that will definitely help you in other topics also. For now, we have understood the complete concept of magnetic effect of electric current, that is part A of electromagnetism. See, sometimes whenever you are learning the concept, you may get confusion. Okay, so just go back and re-watch it, you will understand everything. So immediately after the concept video, just go for the theory solution. The link is available in the description box. Not only the link of that particular video, all the videos of all the chapters are available in the description box. So just go to the description box, you will find the playlist of the particular chapter you are looking for. Thank you.